The first method to form alkyl halides from alkenes is addition of halogen acids such as HCl and HBr. What happens in the reaction is that during the reaction, one carbon of the double bond acquires halogen atom while hydrogen is added to the second carbon of the carbon-carbon double bond. Therefore, these reactions are also called addition across carbon-carbon double bond, because both the new reactants are added to the carbon atoms of the double bond only. That means these are our reaction sites. So what happens, for example, 2-butene, when treated with the HCl, it is converted into 2-chlorobutene. Similarly, if it is treated with HBr, it is converted into 2-bromobutane, whereas when cyclohexene is treated with HCl, then chlorocyclohexane is formed, whereas when it is treated with HBr, bromocyclohexane is formed. So all these alkenes, these are termed as symmetrical alkenes. What do you mean by symmetrical alkenes? All these alkenes can be divided into two equal halves here. But there is an interesting feature which is observed when addition of HBr occurs to unsymmetrical alkenes. For example, 1-propene when treated with HBr, it gives two products. One of them is 2-bromopropane, another one is 1-bromopropane. That is, this is formed as a major product. Almost 90% of the product formed is 2-bromobutane, while 1-bromopropane is the minor product, which only 10% is formed. So what is happening here? What is happening here? And second question is, why two products are formed? And why one is major and other is minor? So the answers to all these three questions, these answers lie in mechanism of the reaction. So let's have a look at the mechanism. What happens in this reaction is that the double bond molecule, that is 1-propene, it at first reacts with the proton, which is provided by the breakage of halogen acid, to form a carbocation. In this case, two carbocations are possible. This one is formed as well as this carbocation is formed. Now this is a secondary carbocation, more stable. This is formed in preference to the primary carbocation, which is less stable. And both these carbocations, when attacked by a bromide ion, they form the product. That is, this product is 2-bromopropane and second one is 1-bromopropane. Since this carbocation formed is more stable, so the reaction likely to follow this route in preference. Therefore, this product is formed as a major product, whereas if reaction goes through this primary carbocation which is less stable, so lesser number of reactants choose this path. Therefore, 1-bromopropane is formed as minor product. Now, this preference that upon addition of alkenes, unsymmetrical alkenes with halogen acid, one is formed as major product, second is formed as minor product. This is what we know as Markovnikov rule. That is, halogen is added to more substituted carbon of the carbon-carbon double bond. This is secondary carbon, this is primary. So, according to Markovnikov rule, in the major product, halogen will be attached to the more substituted, that is secondary carbon, whereas the primary derivative will be formed as minor product. Now, another interesting feature is observed if the same reaction with HBr of 1-propene, it is carried out in the presence of a peroxide, more likely hydrogen peroxide, then this selectivity is reversed in the case of bromine. That means now 2-bromopropane is the minor product, whereas 1-bromopropane is formed as the major product. And again the same question rises that why this is happening. Again, the answer will be provided by the mechanism, and this reaction follows radical mechanism. So, what happens is, due to the presence of peroxide, free radicals are formed. You can represent these radicals by R dot, and these radicals, they further convert HBr molecule into bromine radicals. Happens now, this alkene quickly attacks bromine radical. As a result, again two possibilities arise. If bromine radical attaches to the secondary carbon, then a primary radical is formed. If the bromine atom, it attaches to the primary carbon, then a secondary radical is formed. Now, this primary radical is less stable and this secondary radical is now more stable. Due to this, now the second step is hydrogen radical it will combine with this radical to form the final product. So what is the final product? Again, in the first case it is 2 bromo propane, whereas in the second case it is 1 bromopropane. As we have discussed earlier, all chemical reactions, they follow the path in which there is greater stability. So now more molecules will follow this path which offers greater overall stability. As a result, now this less substituted product is major product, whereas the more substituted product is minor product. So since this now reaction has given you the exactly opposite selectivity, this is what we call anti-Markovnikov rule, and this is observed when HBr is added to alkenes in presence of peroxides. You might note that this is only observed in the case of addition of HBr. Now moving on to the second method. Alkyl halides can be easily formed if halogens are added to alkenes. For example, once again take example of 1 propene. When halogen is added, in case of CCl4 carbon tetrachloride as a solvent, then halogen molecules is added in a manner that each carbon gets 1 halogen atom. That means in this reaction 1,2 halides are formed as product. For example, if you start with cyclohexene in case of chlorine, in carbon tetrachloride as a solvent, what you will get is 1,2-dichlorocyclohexane. If you do the same reaction with bromine and CCl4 as a solvent, you are going to get 1,2-dibromo cyclohexane, and in this reaction there is no worry of selectivity because on both carbons you will get halogen atom. For example, if we start with 2-methyl cyclohexane, which is a unsymmetrical alkene, and you try the reaction with chlorine and CCl4, then there is absolutely no selectivity problems here. What you will get is 1,2-dichloro methyl cyclohexane. Allylic substitution offers another way to produce alkyl halides. So for this reaction, what you need is, you need a carbon-carbon double bond, which is obvious choice. Then you need at least 1 alpha carbon. This carbon is now called allylic carbon, and on this allylic carbon, this is what we call allylic hydrogen. Now this hydrogen is replaced by a halogen when it is exposed. So what happens is, this product is formed. So that means in this reaction, allylic hydrogen is replaced or substituted by halogen atom. So once again, you can take several examples of this. For example, in this case, you can treat it with chlorine and heat it to 773 Kelvin, and due to allylic substitution you will get this product. In case of bromine, NBS is used as a catalyst, and this gives you a selective reaction which gives you 100% allylic product. In case of chlorine, the selectivity is often not there. That means you will get these products as well. But when NBS is used, it gives you selectivity, and you can also note that in allylic substitution, carbon double bond, it does not add up any halogen, while all other methods they include addition of halogen to the carbon double bond.